It's a great pleasure today to introduce Dr. Peter from Hungary. So he fly a long way, 24 hours trip from Europe coming here. But it's so nice to have him here. Peter is really recognized as one of the leading researchers in systems integration, sustainability domains. Very well known for his research work and a lot of efforts, activities across multiple continents. And I'm sure he's going to give a very nice presentation today, focused on, as you can see the title here, Energy Implications of Circular Economy Solutions and Renewable Energy Integration. So please join me to welcome Peter here.
So good afternoon, everyone. I hope you enjoy. Thank you for inviting me, and I hope this would be the basis to further collaborate a little bit more. So the title I've chosen to talk today about is the energy implications of circular economy and how to integrate renewable energy. These things are basically related. And you will see why in the course of the talk. I will spend a couple of minutes only introducing myself and my university. I'm new at this university only not even a year, about 11 months. And I'm very happy I started working with the guys. You will see why. So this is Széchenyi István University. It's located in the city of Győr in Hungary. This is very close to borders with Slovakia and with Austria. And the most convenient airport from there and to there is actually Vienna. You can take Budapest, but Budapest airport is on the wrong side, on the east. So this is about the geographical context. It's a medium-sized university, but it's growing, both in terms of number of students, number of staff, including researchers, and internationality. So most of the academic programs have been already doubled in both Hungarian and English, so it's becoming more and more international in terms of teaching. What is a strong side of the university is a strong collaboration with ODI. ODI has a huge factory in Győr, so the collaboration is strong, and ODI Hungary actually has a stake in the university. University is a private one with a foundation running the university. So if any of you is interested in transportation, it might be a good opportunity. The collaboration brought up quite a stimulus because the students get good scholarships, good challenges, and they've been achieving some wins in competitions for most energy efficient cars. What we have is a science innovation park next door to our university, basically inside the campus, and then in another town a little bit south of this towards Austria and the border with Slovenia, it's called Zalaegerszeg. There is a huge proving ground. Initially it was proving ground only for vehicles of various types, including a motorway strip of about 6 kilometers. But then they added, and it made it, the university made it as an overall innovation park with laboratories for smart city, lecture hall, so it can also host teaching and research. So having the context of that, let's talk about the core topic. So when we talk about circular economy, one has to understand it is about closing the material cycles with nature in the right way. Because what happens is, no matter what you do, material cycles always close. The thing is, when we just dump waste and they don't take care of it, material cycles are closed in the wrong way, which causes pollution and various kinds of problems associated with that. You can give here examples of microplastics pollution, toxic pollution, and so on. So we are talking about closing the cycles in the right way, not spontaneously, but on purpose, purposefully. And another realization we should understand also is in terms of our planetary balance, how energy comes and goes. In terms of the planet, energy comes from the sun. It comes with the highest possible energy quality as photons. Then it gets captured by various terrestrial objects. And this defines a cascade through which, with human activities, we are trying to benefit from it. And in the process, it degrades in quality and then dissipates. Of course, if we set our system boundaries a little bit smaller, we can say that all these terrestrial deposits which actually store energy, we can perceive them as sources, and we perceived coal, petroleum and natural gas as energy sources, and probably many people still do. But if you consider everything from the perspective of the entire planet, these are just deposits, stored energy. It's like a piggy bank. It's good to use, but it's good to preserve as well. And of course, when we burn them, when we use fuels, we release carbon dioxide emissions, which carbon dioxide is a greenhouse gas. But in many cases, it's better if you get a greenhouse gas like methane to burn it than to let it run away. Now, what are the main challenges concerning those contexts? Well, this map, I like it very much, and I typically, when I start thinking about renewables and the footprints, I always start from this point. This is a review paper which we did back in 2015, 2016, and it got published in 2017 with at that time visiting student Lucia. She came to Westpen for about a year. And this represents the international trade equivalent of greenhouse gas footprints. Basically, when goods are produced, certain footprints are emitted, and when you ship the goods to the users actually cause those footprints to be emitted. So this has to be taken into account. So we have a huge international trade. I'm not sure how much of it is actually necessary. I'm not sure how much of those goods are useful, and whether it wouldn't be better to be produced closer to the users. But this is the current setup. International Trade Organization allows it, and it works. So we need to account for greenhouse gas footprints, but we also have other footprints. This is just one example how we would consider footprints. We can consider land footprints, climate, health footprints, ecosystem impacts. When we say ecosystem, this is actually a group of footprints where it can be, water pollution, toxicity to the ecosystem, and so on. There are various indicators. So we need to take care of the footprints, both in production, but also in logistics and the overall supply chains. When it comes to regional resource management, this is a work which we started with our student LAM back in 2007, and in 2010 he successfully defended his thesis. And what we realized is renewable energy is captured over areas. So this creates immediately a spatial development problem. And the thing is, capturing energy from an area in the form of either biomass or, if you want, even photovoltaics or wind, it creates also a logistics problem how to concentrate this energy and deliver it to the potential users. So we came up with this zoning development and realized that we need to minimize the overhead of greenhouse gas footprints to actually transport the energy or the energy carriers. So we came up with this so-called clustering technique to basically, you can see it here, minimize the connections between more distant locations, which would result in more efficient energy supply. And later we did a few case studies, and this is a follow-up work of LAM based on a case study in Malaysia. In Malaysia, they have a special problem about this. They have huge oil palm farms for producing this palm oil. But after producing the palm oil, they have huge biomass excess, and they have to somehow treat it, because otherwise it becomes waste. It decays and it emits a runaway methane body, which is not too good. So they have to take care of it, either digest it forcefully or burn this biomass, somehow utilize it to prevent bigger climate problems. So this example here is to say green is not always good for the environment. It has to be done in the right way to be good. Okay. So here we come to the point where we can discuss circular economy. When we say circular economy, there are several levels here. First, the simplest way of recycling things is actually to reuse them. This means recycling the value of the products. For example, take plastic bags. What is better when you shop, plastic bags or paper bags? Many people would say paper, not really. Because to produce paper bags, you get a lot of water footprint released. Plastic is dangerous, but up to 5, 6 to 10 uses, you can still reuse them. And if you dispose the plastic bag on time, it can be incinerated, and you would prevent the big pollution of microplastics, and at the same time you would save a lot of greenhouse gas footprints if you throw the bag immediately, compared to if you throw the bag immediately. So the first thing to do is reuse as much as is safe or possible. Second level is what we know as recycling. Basically, this is materials recycling. This involves some processing. This means this processing would consume resources and would release emissions of various substances. And the third level is when you can't do anything with those materials, you should either bury them, which has absolutely no recycling value, or perform energy valorization. So this is the visualization of the problem. One can start with extracting virgin materials from nature, then go through the entire life cycle of initial material processing, producing various goods and services, use them, consume the products, then some waste of those is collected, and then you get the disposal or waste processing. But what we are aiming for is the bulk of materials to come back into circulation to prevent the extraction of virgin materials. This is the principal idea. And here you can see smaller circles drawn which represent local product reuse, like here, or material recycling, or in industry, one can have so-called process integration, which basically is a reuse of various waste streams at the stage of production. The simplest process integration is heat integration, where waste heat is delivered to heat demands, and this saves simultaneously heating, cooling utilities, and greenhouse gas emissions. So you see it's a complex problem which has to be solved using network modeling and network optimization. Now, how to deal with it? If we focus here on this outline part, where we would like to make the recycling, yes, the more we integrate, the more we go to wider areas, really physically areas, and longer supply chains. So this increases the opportunities, but it also increases the overheads of doing so. These overheads can be financial in terms of cost, or they can be in terms of resource consumption, or in terms of emissions. So in this sense, if we imagine we would like to solve this as an optimization problem, as an optimization task, we need an objective function. So we would like to model our footprints as such, as footprints, as emissions and environmental impacts, but those can be mapped to costs, either costs for cleaning or costs for prevention, so these would define eco-costs. Then various integration techniques can bring savings, both in resource consumption and money. So this can be defined as eco-benefits. So once we have these impacts defined as in their monetary equivalents, we can add them to our objective function for economic optimization, which gives us the full picture when we want our optimal processes. So the key point here is to account for all significant footprints, not all footprints. And this is a tricky task. It's more an art than a science. It requires human judgment. Okay? And another thing to understand is when we say significant footprints, we are working with people, we are working with experts, so we need various stakeholders, and those stakeholders have to exercise their judgment as well. So when we focus on our recycling activities, I would like to use this kind of map where we have waste, which we consider as resource. This waste is somehow processed by various options. So this requires various paths of processing, and secondary products are produced from these secondary raw materials, but they're in competition with the products produced from virgin materials. Okay? So that's why I like this mapping, because we can assess what is better, this or the other, why it can be better or worse. We already know that extracting virgin resources and releasing emissions into the environment bears some cost in terms of pollution, cost in terms of money. But also here, recycling. Many people don't realize it and say, let's recycle the more, the better. Well, yes and no. Because when you perform the recycling activities, no matter what you do, you spend at least energy. And in many cases, you also spend water, probably other resources. And in this process, emissions are released as well. Now, the bigger question is, what releases actually less emissions and what uses less resources? Recycling or using from virgin sources to produce products? The intuitive answer would be yes, recycling would be better, but this is not always the case. Okay? So a few important points before I show you how we modeled the issue with our students. And maybe you can both criticize, elaborate, discuss. Industrial and urban symbiosis systems inevitably use resources and they cause footprints. Okay. Maybe this happens at a lower rate than virgin resource use. So this can be expressed in monetary costs, in footprints, exergy, footprints, and similar. And this requires sensitivity analysis to determine how much should be recycled, how much is better, how much is not better. Okay, so this is the result what we obtained for the case study of trying to valorize and recycle materials from municipal solid waste. When we tried to track, so each of these points here is actually an optimization solution for when we set up, we want to say obtain 10% circularity in terms of materials or total circularity index. In this case, this is a composite index between materials recycling and energy valorization. So when we optimized for various settings of this composite index, we found out that actually our minimum in terms of total annual cost was around 50% recycling. Okay, and more specifically here you get the zoomed in version. It's between 45 and 50%. This is in terms of monetary cost. But if we model how much greenhouse gas footprint is reduced by such an activity, we get this picture. This says the more we recycle, the better. Okay? So this is because much of the municipal solid waste content can actually be valorized by generating heat and using this heat either directly for heating or for power generation. That's why the more we recycle municipal waste, the better in terms of greenhouse gas emission reduction. But this is not the case for water footprint. For water footprint, we get again a problem. And the maximum reduction of water footprint happens even at lower recycling rate than the economic optimization. It's about 35, 36%. This is because obviously many operations require cleaning, washing, and requires water treatment after that. So why do we get these results? Initially I was thinking, okay, maybe I get 80-90% recycling rate as the optimal. Apparently it happens 35 to 40%, 45. Then we started analyzing the causes of this. So the causes are that we have limited options in our case study. Much of the materials are not well designed, so they're difficult to recycle. This immediately goes to landfill. There are many materials which you cannot possibly recycle. Typically these are plastic-based composites. Most famous analogy is actually those blades of the current wind turbines. They are still not very easy to recycle. The best one can do is do some downcycling. I basically transform that material to another use. But after that reuse, after that it has to be buried. So we have a lot of materials which cannot be recycled. Then many of those which can be recycled, their processing causes site pollution, which ramps up the water footprint and the cost. So in that sense, we have one source with limited options for recycling, while we have many potential product users. So this is a structural issue. So we have a single source of secondary raw materials, limited availability, constrained pool of demands, limited interaction. So we need to consider multiple actors. We need new degrees of freedoms, it means new sources, new sinks, new processing paths, it means new technologies. Okay, and we need a novel method for targeting and to guide us as a compass. Well, one option of such new technology development I found is processing of sewage sludge and valorizing the energy content of sewage sludge. So this is a good step. And that energy can be valorized in various ways. First, directly as heat, or it can go to power generation, and then you can supply the power to the grid or directly to customers. And of course, it can be combined with harvesting renewables. So we come up to the point where we have a mapping of recycling paths, fresh paths, but what is better? What is better in terms of energy, how we can do the energy modeling in a way that to allow energy cascading in the most efficient way so that we are able to increase our recycling rate and reduce pollution. This is where we went for so-called energy quality modeling and energy quality pinch. And this includes industrial parks. We don't have time to delve into what is pinch analysis, but you can check it out, pinch analysis, this phrase, and the name Bodeling Hof, it will pop up. It's about heat integration and how to combine heating and cooling demands in a way that to minimize external utilities in terms of fuels and external cooling. So coming back to our mapping for the recycling, we would like to identify the processing paths in our system and group those paths into those which have energy excess and those which have energy deficit, and try to figure out what is the energy quality of that energy provided or energy required, and model it in terms of energy quality. Now, energy quality is a tricky concept. So far what we use is this definition here, taking the ratio or the fraction of exergy in the energy flow. Why I do that? Because if we just take temperature, we can model only heat flows. But energy comes in several forms. It comes as heating, cooling, but it comes also as electricity, it comes as electromagnetic radiation and so on, and mechanical. So we need to be able to compare all these options, including pressure drops for pumping. So once we have grouped various energy sources and energy sources and energy sinks of various energy quality level, we can actually use this type of curves, and the more we overlap the curves, the more the integration, the more we save energy. Once we make our recycling process or any industrial symbiosis or urban symbiosis more efficient, the better, the more we reduce the cost footprint. So this is the procedure. I think, yes, if anybody is interested, please let me know. The presentation is available, no problem if you want to get it, and we can discuss more, but this is the procedure to construct those curves. So once we construct the curves, we would like to overlap them. Okay. Then we define some pinch point which identifies the maximum possible overlap, and then by how much the curves do not overlap, we have the residual energy demands, either to supply energy or waste energy, which is going to be rejected by the system, and we have to think how to deal with it later. Because the more this is wasted, the more here we use as an input. So now a few examples. this is a logistics-dominated problem of reverse logistics and in urban and industrial symbiosis case. Waste is collected and tried to be valorized. And when we did energy quality bench analysis, here is what happens. We have a lot of waste heat from the incineration, but we have huge deficit in energy at very high energy quality for the logistics. So this determines a logistics-dominated problem, and we have to think how to solve this issue by either distributing the processing or providing a way how to reuse this energy further when after it's consumed. But if we want to integrate a few processes on a single site, then logistics doesn't get so dominant. Our curves can be used to actually stack processes and try to figure out what is the potential benefit. We successfully applied this also to managing energy in buildings. This is so-called project Race Heat. Basically, it's a demonstration project where we have various kind of solar energy harvesting devices like solar thermal panels, photovoltaic panels which only produce electricity, and then photovoltaic thermal panels which produce electricity and warm water, not hot water, warm water about 35 degrees. And then this can be used for supplying the energy to the building. And we are just finishing the project. Everything is recorded and will be made public after the project completion as data. And basically what happens is we get a really nearly balanced system using the solar energy, and this is for Polish climate. Poland as a climate is a little bit like here, even maybe a little bit cooler. So even for Polish climate, we get about 80 to 90% of the energy needs of the building served by solar energy all year round on an annual basis, which is very beneficial. So you can see modeling energy quality in terms of supply and demand helps to analyze the system and generate options which further can be subjected to optimization. So this is our compass. Now, what can be contributions to the solution? First, when we talk about circular economy and symbiosis, we need to realize there are multiple actors and multiple actor types. This is a dynamic system, so everything varies in time, both supply and demands. We need fair and transparent allocation of footprints and the related costs. We would like to maximize the profit, we would like to maximize eco-benefit and sustainability. So, and this should go across all sustainability dimensions. Now, this defines a few strategic challenges. We have various contexts and various scopes, municipal scope, regional scope, international. So when we need to implement such processes, this requires a lot of coordination. So it requires the symbiosis to be performed in networks, and those networks have to be smart, because here we are talking about time variations and things happen too fast to be delegated to manual contracting and manual deals. So basically we're coming to the realization we need smart symbiosis networks where we need both process integration and digitalization. Process integration is what we are aiming for reducing resource use and footprints, and digitalization is the enabler. Okay. We did a small case study about this for industrial site where there are different actors on the site. So basically all plants are separate companies. And we discovered that without a transparent market system which enables the trading, not much integration can be done, and the enabler in terms of a blockchain-based trading system which sets up a trusted environment helps to save a lot of energy just from operation. So we need to achieve higher circularity and benefits using integration as the tool, as the method, and digitalization and a smart market as the enabler. We need to widen the area of integration and increase the scale. So we need transparent account, and this is where the blockchain comes in. Now, what else? Well, we need some technologies which would enable such efficient integration or renewable harvesting. MOFs and COFs. This is important technology to watch because these are porous materials which can be tuned by design, and they can help in various contexts. The most obvious contexts demonstrated so far, these are water harvesting, hydrogen or other storage of gases, gas separation, and so on. Microfluidic processing systems, they can be useful for concentrating distributed resources into valuable products and transporting only the valuable products which are in smaller amounts. In essence, the metaphor is not to transport waste or biomass to central locations, but transport fuels and valuable products which have much higher density. And electrochemical conversions of carbon dioxide can be useful if you have a lot of electricity generated by renewables, but when you have low consumption. So this can be used for direct CO2 recycling. The processes have to behave like energy storages, and one good example is when you have energy-intensive processes which don't have precise needs to be scheduled, which can be postponed and put or moved forward. They can be adjusted to be activated during periods of energy excess, so this would give a smoother schedule with much lower energy requirement. So the main principle is maximize the energy density of the useful products or useful product density at the smallest scale possible. Okay, just to give you the example why I like the MOF so much. Very high specific area. They're already aiming for 10,000 square meters per gram. And it can be used, as I said, in various contexts, including gas separation and energy storage and gas storage. Here is a good example what can be done. If it's done in the most direct way, there are few papers which report reasonably good water harvesting from air, but at some expense of energy. But if you just oversize the device with more active material, the device can be made passive, which means nearly zero energy, and the only environmental footprint of such devices would come only on life cycle basis, only from producing it or destroying it at the end of service. It can be used for other purposes, including waste processing, and microfluidics is also an important step. I haven't delved into it yet, but the very fact that one can implement chemical and other processes at small scale, it can be very beneficial in the task of implementing distributed processing, and this distributed processing to concentrate streams, either in terms of fuel output or product output. To conclude, we can reap tangible achievements in circular economy. There are good achievements and research prototypes. But there are still many challenges, especially to increase the circularity rate. We can use tools as energy quality pinch and smart symbiosis networks. And this allows to enact transparency, and transactional activities can be conducted, which makes digitalization as the enabler for the integration. We also need novel technologies, so the task is not solved yet. Without the novel technologies, such goals are too ambitious. We need to aim for circularity rates beyond 50% if we are going to achieve sustainable development. So much about the conclusions. A few topics which probably we can discuss later. This is what we've been discussing last night with my student team, aiming for the waste processing from energy building systems. She wants to go for a more detailed life cycle assessment, going for what is this example of so-called dynamic life cycle analysis in buildings. Yeah, probably we can meet in Malaysia next year. I would very much like to see some of you. So thank you for the attention.
Thank you so much. Coming. A couple minutes for some quick questions.
Thank you for the presentation. Regarding the building system you analyzed, and it said this kind of distributed energy sources for each building is going to be beneficial. But the other thing is that because you have expertise in life cycle assessment, but producing all these energy storage or energy production in renewable ones, they require another resources. So is it mentioned, is it considered in your research of the life cycle of producing those?
Yes. Actually, this is it's a right question, first of all. One of the work packages in our project was exactly on a full life cycle assessment. I don't have the time to put it here, but basically because when you use photovoltaics, your only footprints come only from production and dismantling phases. And when you spread it over the service life of 20, 25 years, it's a very low footprint compared to other options. So yes, it's very beneficial. Of course, there are challenges there. This is why we want to study the recycling from those panels, because it's still very expensive to do it. And I believe this is both a challenge and a very, very big opportunity.
Thank you.
So you demonstrated that we can do things in a lot better ways, you know, that there are improvements are possible. So how do people make this happen in Hungary? You know, markets are incomplete, we don't charge for carbon, you name it. So is the government sort of setting standards, or is it not happening? I mean, what's going on?
Well, at the moment, if you think in terms of regulation and policy, it's taking place at European Union level. And they set some targets, which in most cases, I don't think they are too realistic. Very big emphasis is put, say, on carbon capture, which I don't think it's any good, simply because even if you assume that you successfully capture it, it would, where to store so much? It's crazy.
This seems to be an area where sort of regional solutions would make a lot more sense than sort of trying to have one.
For me, the way is to push governments to adopt and put focus on efficiency. passive, when you go to buildings, for example, because industry is a different ballgame, but say to buildings, it's pretty clear. With more improvements to make the buildings more passive, that 70 to 90% renewable supply rate can become 100%. The buildings can even become prosumers. It's not so complicated. And this is a good use of any resource, including money. To capture things, even hydrogen storage is good, but it can't be overblown. Because the round-trip efficiency of hydrogen storage would be how much? Upper bound is 50%. If you want energy storage in hydrogen, upper bound. Because, and this is if you assume energy is retrieved from the hydrogen using fuel cells. So for me, the focus must be on efficiency and preventing waste. If we eat food, we should eat as much not to throw away. Anything thrown away is actually resource wasted and additional pollution. So this would be the first step. Second step is any inevitable waste should be processed in a smart way. It has to be reused at the first possible opportunity. I think we are very far from it, both in Hungarian context and European Union context. You can tell me about the US. All right.
Have you applied or have you seen it applied, the principles of integration, finding the optimal amount of integration for different types of systems that might not be about energy or material use?
What would you like to integrate?
I'm thinking of like different, I guess in general, different like infrastructure. In my case, I guess would be energy, but like more physically, mechanically, for example.
Well, you can reuse products. You can supply waste materials which are waste for one industry to another.
I guess do you
And you
use the
can do
same pinch
recycling.
analysis?
But in all these activities, you have a common principle. You need to make energy, you need to use water to transform those streams into something useful. Even if you assume complete reusability, typically the demands are in a different location than the supplies. So at least you will have energy spent for transportation. That's why I emphasize energy so much, because it's the key. If you have clean energy at reasonable cost, even if it's not cheaper, but at reasonable cost, you can do a lot of footprint minimization.
Yeah, please.
So we have some problems in this state about space heating. And at the moment, we think that air source heat pumps are a good idea. But I saw that, you know, you had solar thermal, you
Yes.
had geothermal, sort of what's the mix of space heating in terms of the source that you have in Hungary?
Well, first of all, it depends on the climate. Now here, you mean the current location here, in this state of New York?
Yeah.
Well, it's pretty north and a similar climate to Central to Northern Europe.
Yeah.
Well, first of all, when you minimize the demand, whatever method for heating you use, it becomes less significant. For example, I can speak from personal experience. I live in a very well heated, insulated building. Even in the coldest winter, with minus something degrees Celsius, I just turn on the heating for half an hour in the evening. That's it. So in that context, basically most of your heat with well passive building would would go for hot water and a little bit of space heating. So this is the demand side. Air source heat pump is a good solution because it requires less investment than ground source heat pump. It's less efficient, no question here. Plus, if outdoors temperature gets too cold, at some point the external heat exchanger, when the heat pump works in heating mode, not in cooling mode, yes? So in that case, the external heat exchanger gets clogged with ice. And when this happens, it doesn't stop working, but it starts working as a simple resistive heater. That's the problem. So if you get to, say, a colder climate like Alaska maybe, or northern Canada, probably there the better solution will be ground source heat pump. But here I think air source heat pump should be adequate, more or less.
Cold winters, it could be an issue.
Sorry?
In a very cold days, in the winter,
Yes,
air source hookup could be an issue here. because
yes,
it's
well,
too
it
cold
depends,
outside.
yes.
So are there standards
If-
on
if-
new buildings?
If you have high risk of freezing, you have to go to the ground source heat pump.
So are there standards on new buildings they have to meet, you know,
Yes,
are there?
well, there are already standards about this and they have to meet those standards, yes. I live in such a building and it's built in 2010. But the problem comes with ventilation, you can't just close the windows.
That's always a problem. Yeah. Anyway, I think we are running out of time, so let's thank Dr. Brewer again for a nice talk, and this is last. So if you're around to talk, if there's any questions, to reach out. Photos look beautiful. Maybe you guys should consider visiting Malaysia next year.
You're all invited.
Yeah.